Hello everyone, and welcome to my flash talk on pumped heat energy storage. So why use pumped heat? It's very similar to pumped hydro in terms of cost and efficiency. As you can see on this chart on the top left, PHES is pumped heat energy storage and PHS is pumped hydro storage, and they're close to each other in being the cheapest in terms of cost per unit of energy. Batteries are kind of in the middle there, and hydrogen is on the more expensive side of the chart. Pumped heat is also deployable anywhere. So when you're comparing it to pumped hydro, you can look at the bottom two pictures. The pumped heat system is on the left and pumped hydro dam is on the right. So you don't need the geological features that a pumped hydro dam would need. A single unit for a pumped heat system is much smaller and can go pretty much anywhere. And these systems also have a thermal energy potential where you can convert the energy either back to electricity, or you can just use the thermal heat to either warm up or cool down a large structure. The components of a pumped heat energy storage system consists of two low-cost, usually steel tanks filled with mineral particulate, which is gravel-sized particles of either crushed rock or ceramic normally. Also a heat pump for charging and a heat engine for discharging. The working fluid, which is usually argon gas, because a monatomic gas such as argon is ideal as the working gas as it heats and cools much more than air for the same pressure increase or drop, which in turn significantly reduces the storage cost. So for how these systems work, during the charging stage, the argon at ambient pressure and temperature enters the compressor. The compressor is driven by a motor generator using the electricity which needs to be stored, and this argon is compressed to 12 bar and 500 degrees Celsius. It enters the top of the hot storage vessel and flows slowly through the particulate, heating the particulate and itself cooling. As the particulate heats up, a hot front moves down the tank, and at the bottom of the tank, the argon still exists at 12 bar, but now back at ambient temperature. And then this gas enters the expander, which when it is expanded back to ambient pressure, it cools down to minus 160 degrees Celsius. And then the argon enters the bottom of the cold vessel, flows slowly upwards, cooling the particulate and itself being warmed, where it leaves the top of the tank back at ambient pressure and temperature. And these two tanks will stay at their respective temperatures, the hot one being 500 degrees Celsius and the cold one being minus 160 degrees Celsius. They'll stay like that for up to 8 hours. And now during the discharging phase, when the energy is demanded to recover the power, the gas flow is just reversed, and the argon at ambient temperature and pressure enters the cold tank and flows slowly down through it, warming the particulate, and therefore the gas becomes cold. And then it leaves the bottom of the tank at 160 degrees Celsius, where it enters the compressor, and it is then compressed to 12 bar, heating back up to ambient temperature. And then this enters the bottom of the hot tank, where it flows upwards, cooling the particulate and warming the gas to 500 degrees Celsius. And then the hot pressurized gas then enters the expander, where it's given up as energy and produces work, which drives the motor generator to return back to electricity. So in conclusion, these pumped heat energy storage systems can address markets that require response time in the region of minutes upwards. These systems use gravel or ceramic as the storage medium, so it offers a very low-cost storage solution, and there are no potential supply constraints on any of the materials used in these systems. And plant size is expected to range from 2 to 5 megawatts per unit, but groupings of these units are possible, which can provide gigawatt-sized installations. And then there's the main advantage, I would say, over pumped hydro, which is the deployability of these systems. You can pretty much implement them anywhere, and they would be really useful for anywhere where renewable energy is being harnessed, whether it's wind or solar. And then there's the high efficiency of these systems, which is estimated to be in the potential of 75 to 80% efficient in terms of incoming energy and releasing that energy back out on demand. So last, here's a list of references that I used. If you guys have any questions or comments, feel free to leave them on Blackboard. I'll try to answer them to the best of my ability. But thank you guys for listening. Cheers.